segment, we'll be learning how to show. Hello, everyone. In today's segment, we'll be learning how to show that the escape speed from the surface of a planet of uniform density is proportional to the radius of the planet. Now, what is escape speed? Now, escape speed is when we have an object projected upward from the surface of the Earth with a large enough velocity. When an object is given a large enough velocity for it to escape from the gravitational pull, of the Earth, the velocity will be called escape velocity. So if we have an object mass, you know, projected upward from the surface of the Earth with a large enough velocity, then it can soar off into space and never return. So when the object does not return, to the point of projection, okay, then it means that the velocity or the speed is what is called escape velocity or escape speed. Escape speed is the minimum speed needed by a body to escape from the gravitational pull of a planet without further propulsion. Okay, so in this video, we'll be learning how to show that the escape speed from the surface of a planet of uniform density is proportional to the radius of the planet. Now, let me use another context, to explain escape speed. Let's use diagram. Okay, let's say we have the Earth. Okay, we have the Earth. This is the Earth, and this is the center of the Earth. And then we know the distance from the center of the Earth to the circumference or to the surface of the Earth is what? Is the radius. So we have the radius of the Earth. Now, let's say we have a satellite, okay, a satellite revolving around the Earth. So we have orbit of satellite. We have orbit of satellite. So let's say this is the satellite. Okay, let me use this dot. And then we have the mass. Okay, so it is revolving around the Earth. So let me extend this. So this will be called, let's use X to represent this. So orbit of satellite. So a satellite revolving around the Earth, okay, must possess two energies, and the two energies will be both the kinetic energy and potential energy. So the kinetic energy will be due to its motion, that's the motion of the satellite. Then the potential energy will be due to the gravitational field of the Earth. Okay, so that's when we talk about the escape velocity. Now, to be able to find the escape velocity, okay, that is to derive escape velocity, we're going to apply the principle of conservation of energy. That is, the total energy will be equals to the sum of the kinetic energy, okay, due to its motion, due to the motion of the satellite, plus the what? The potential energy, okay, due to the what? Due to the gravitational field of the Earth. So now in this case, so we have a satellite, okay, like I said, a satellite, okay, revolving, okay, revolving around the Earth, okay, revolving around the Earth, will possess both kinetic energy, okay, both kinetic energy and what we call potential energy. But the potential energy in this case is what we call the gravitational potential energy. Okay, so yes, so like I said, if we have an object mass m, okay, projected vertically upward with an initial velocity, let me put it that way, with an initial velocity vi, okay, I want to use it to explain this, okay. So now by applying, let's put it this way, by applying the conservation, okay, the principle of conservation of what? Conservation of energy. Conservation of energy, okay. When an object, like this object, an object an object of mass m is projected, okay, upward, is projected upward from the surface, of the earth, with an initial speed v. So let me use the v to be what? Vi. Okay, that's the initial speed vi. So to be able to derive the formula for escape speed, now it is important for us to know that now for this vi to become the escape speed, it means the first thing is we need to neglect air resistance, and also to assume that this value, the value of vi, is just large enough to allow the object to what? To reach infinity at a speed of 0. So when the speed, when we say the speed is equals to 0, so that means the final velocity will be equals to 0. You know, according to the principle of conservation of energy, okay, we have that the total energy will be equals to the initial kinetic energy plus the what? The gravitational potential energy. So we have the initial gravitational potential energy. So when the final velocity is equals to 0, then the kinetic energy will be equals to what? 0. Okay, so and that will be because the object will be at an infinite distance, okay, from the earth surface. So that's that. Okay, then the gravitational potential energy is also 0 because the reciprocal, okay, I'm going to explain that. So now, so what we have here is the kinetic energy and the what? Potential energy. So we have the kinetic energy, okay, which is the initial kinetic energy, to be 1/2 multiplied by mV². Okay, you know, the energy possessed by a body by virtue of its mass and velocity is what we call kinetic energy. Now, then the gravitational potential energy, okay, the gravitational potential energy will be negative g mass of earth, okay, multiplied by the mass of the planet or the satellite, okay, over what? Over r. Now, you know, when we talk about gravitational potential energy is the work evolved, okay, in bringing an object mass m from infinity to a point in the gravitational field of the earth. Okay, and to be able to derive this formula, we're going to apply the concept of integration, you know, to be able to prove that. So this is the gravitational potential energy associated with a body of mass m at a distance r from the center, from the what? From the surface of the earth. Okay, and in this case, this radius, okay, this radius will be what? Will be greater than the radius of the earth. It will be greater than the radius of the earth. Okay, so now, so according to this principle, that's the principle of conservation of energy. So we're going to have the total energy to be equals to the kinetic energy, which is 1/2 of mvi² minus the mass of the earth. This is the gravitational constant or universal constant. So we have me multiplied by m over r. Now, I said the total energy is equals to sum of the initial kinetic energy and the what? Potential energy, which is the gravitational potential energy. But when the final velocity, okay, when Ke, you know, note, when the body is at an infinite distance from the earth, okay, when it is at an infinite distance from the earth, okay, from the earth surface, okay, the kinetic energy will be 0. That will be because the final velocity is what? 0. And also the gravitational potential energy, this is the final kinetic energy, okay? So the gravitational potential energy, which is the final gravitational potential energy, will be 0, okay? as the reciprocal of r, okay, approaches, as this approaches, zero, okay, and r approaches infinity. So therefore, it means that the satellite, okay, we what? We leave the orbit of the Earth. That is what I'm trying to explain here. So when the satellite leaves the orbit of the Earth, so it means the total energy will be equals to zero. So when we write the total energy, that means from, we can say from the total energy equals to 1/2 of the mass, okay, VI square negative GME, okay, multiplied by M over R. So when this is equals to zero, it means that the satellite, okay, leaves the orbit of the Earth. And that is when we now have zero equals to 1/2 of MVI square negative GME, okay, multiplied by M over what? Over R. So now we can then write this to be 1/2 of mvi to the square, okay, equals to what? GME multiplied by what? M over what? Over R. Remember I said when the initial velocity is large enough to just allow the what? The object to reach infinity at a speed equals to zero, which I already explained here. When the velocity is equals to what? Zero, or at zero speed, then we can then write this. So vi will now be equals to the what? Escape velocity. So which means from here we can say that 1/2 of m ve square equals to gm mass of the Earth multiplied by the mass of the what? The satellite. So we have it over what? Over r. So this will cancel out from both sides. Then when we multiply, so we're going to have the escape velocity to be equals to, the escape velocity square will be equals to 2gme, okay, over what? Over r. So when we take the square root of both sides, okay, when we take the square root of both sides, so we are going to have the square root of ve square equals to the square root of 2gme over what? Over r. This is when we take square roots, okay, of both sides, okay, when we take square root of both sides. So this will become ve equals to the square root of 2gme, okay, over what? Over r. Okay, now moving on. So we have here that now, we have from the surface of a planet of uniform density. So we are going to relate mass and density now. So we know that relate mass and density. Now we know that for density, okay, let's manage the space. So we have for dense now, okay, to relate mass and density, okay. So we have so we are going to write mass, no, we're going to write the density equals to mass over volume. So we're going to express the mass of the Earth, okay, in terms of what? In terms of density. So we can say that mass of the Earth equals to density multiplied by what? Multiplied by volume. Now we know the Earth to be what? Spherical, okay. So we are going to use the volume of a sphere, which is 4/3 pi r e to the what? To the cube. That is the volume of sphere. So we're going to put that here. So which means mass of the Earth will be equals to density multiplied by the volume, which is 4/3 pi r e to the what? To the cube. So we're going to plug in, this is going to come here. Okay, so we substitute. Okay, so we are going to substitute. So remember, okay, this is the first equation. This is the first equation, okay? Now that's the first equation. Now this is the second equation, okay? That's the second equation. Now we now have the third equation. This is the third equation. So here we have the fourth equation. So substitute let's substitute equation 4, okay, into equation what? Equation 3. So we then have the velocity, which is the escape velocity, to be 2 GME, okay, that is density 4/3, okay, pi r, okay, pi r e to the cube. So in this case, the small r becomes what? The big R. Okay, the small r becomes a big R in this case. So we are going to have, okay, we are going to have over r, because r is now equals to what? Re. Remember, I said in the case of gravitational potential energy, okay, in the case of gravitational potential energy, r is greater than, that small r is greater than what? The radius of the earth, okay? So in this case, it's going to be what? Re. So 1 Re we cancel out from here. So we are going to have the escape velocity to be equals to the square root of, so this will be 8 over, so the square root of 4, that's 2, okay? So we're going to have this to be 2, that is square root of 4 is 2. Okay, so this will be 8/3. Okay, 8/3. Then G, that's 8/3. G pi what? R raised to Re raised to the power of what? Raised to the power of 2. Let's confirm that. Okay, we have 2 times 4, that's 8, multiplied by G. Okay, then also multiply by density. Okay, because we have here that mass of the earth equals to density times volume of the earth. And because the earth is spherical, okay, so if we know that volume of a sphere, okay, this is volume of a sphere. So because we have it to be in, to be in terms of the earth, it will be radius of the earth, okay, raised to the power of 3. So now we just show that the velocity, the escape velocity from the surface of a planet of uniform density is proportional to the radius of the planet. So this will be the radius of the planet. And why I made use of the small r is because when I explain gravitational potential energy, I said the gravitational potential energy associated with a body of mass m at a distance r from the what? From the surface of the earth, okay, is what we have here as negative GME times m over what? Over r. But in this case, I made r to be equals to what? Re. Okay, I made r to be equals to Re. So now, so from here we know that the square of Re will be r. So we are going to bring it out. So we have Ve to be equals to Re, then the square root of, so that will be the square root of, we have the square root of 8/3, okay, G pi density. So we can also have, it this way, okay, apart from how we have it here, okay. And we have come to the end of this session. The noblest pleasure is the joy of understanding. Bye bye. Thank you.